All right, welcome. Today, we're diving into a really critical safety step in laboratory testing, the inhibition and enhancement test. Now, I want you to think of it like the sound check before a huge concert. It's that one crucial step that makes sure the results you get are results you can actually trust.
And that right there is the big question we're tackling. Just imagine this. You run a critical safety test, but what if something in your sample is secretly messing with the results? How would you even know? Well, this simple preliminary test is designed to answer that exact question and make sure your main test isn't, lying to you.
So let's really dig into this whole sound check idea. A sound engineer at a concert, they have to stop two main things, right? Muffled instruments that you can't hear, and that awful high-pitched feedback screech. It is exactly the same principle here. We have to check if our sample is inhibiting or muffling the endotoxin signal we're trying to find, or if it's enhancing it, creating that false feedback. This test just makes sure the stage is perfectly set for an accurate result.
So, here's our game plan for today. First, we're going to talk about why this pretest is so incredibly important. Then, we'll meet the key players, the different solutions that make this whole thing work. After that, we'll walk through the test itself, step by step. Then we'll learn how to actually read the results, and finally, we'll cover what to do if you run into a problem and find some interference.
Okay, so let's jump right into the why. The whole point of the bacterial endotoxin test is safety, and you just can't have safety without accuracy. This initial check is basically the gatekeeper for that accuracy.
So there are really two ways our sample can throw things off. First, you've got inhibition. This is where something in the sample kind of puts a pillow over the speaker. It muffles or totally masks the endotoxin signal. The big danger here? A false negative. You think a product is safe when it's actually contaminated. On the flip side, you have enhancement. This is that feedback screech. Something in the sample is artificially boosting the signal, which can give you a false positive, and that means a perfectly good batch of product could get thrown out. Both are really costly mistakes that we have to avoid.
So to figure out if we have any of this interference going on, we need a few, let's call them key players. Let's meet the four essential solutions that are really at the heart of this whole experiment.
Okay, this table lays out our cast of characters. Let's start with our controls. Solution A, up at the top, is just your sample by itself. This is to check if it's already contaminated from the get-go. And then at the bottom, Solution D is just pure water, which makes sure our whole test setup is clean. Now for the main event. Look at Solution C. That's pure water with a known amount of endotoxin added. Think of this as our perfect signal, our benchmark. And finally, you have Solution B. That's our sample, also spiked with the exact same amount of endotoxin. This is where we actually look for that interference.
And this, right here, is what it all boils down to. The whole test is about weighing the reaction in our sample, Solution B, against the reaction in our perfect control, Solution C. Is the signal from our sample weaker, stronger, or is it just right? Answering that one question tells us everything we need to know.
Okay, so we've met the players, we know the goal, so how do we actually do this in the lab? It's really a pretty straightforward process when you see it broken down like this.
First up, Step 1, you get everything ready, preparing your solutions in their labeled tubes. Then, in Step 2, you add the magic ingredient, the LAL reagent. This is the stuff that actually reacts with any endotoxin present. After that, as you can see in Step 3, they all go into an incubator at a nice and cozy 37 degrees Celsius for exactly 1 hour. And finally, the moment of truth. In Step 4, we flip each tube upside down. If a solid gel has formed and it stays put, that's a positive result. If it's still a liquid, it's negative. Simple as that.
So, after that hour is up, it's time to read the results. How do we know if our sound check actually passed? Okay, first things first, before we get ahead of ourselves, we have to check our controls. Solutions A and D, that's our sample by itself, and our pure water, they both have to come out negative. They should stay liquid. If either one of them forms a gel, it means something was contaminated from the start, and, well, the whole test is a bust. You've got to scrap it and start over.
All right, so our controls are good. Now we can finally focus on our two main players, B and C. To get a super precise result, labs will actually run a series of dilutions to find the exact point where the reaction stops, and this result is called the geometric mean endpoint. Now, I know it sounds complicated, but just think of it as a very, very accurate way to measure the loudness of the endotoxin signal in each of those solutions.
And that calculation brings us to this right here, what I like to call the golden window. The Greek letter you see, lambda, just represents the labeled sensitivity of our test. Basically, the smallest amount of endotoxin it's designed to detect. For a test to be valid, our result has to fall between half of that value and double that value.
This range is there to account for normal, expected variation in any experiment. Anything outside of it, though, suggests something's off.
So this slide shows us exactly what a pass looks like. Our perfect signal, solution C, sets the benchmark. The result we get from our sample, solution B, has to land somewhere in that sweet spot, no lower than half the lambda value and no higher than double. If it lands right there, congratulations, your sample has passed the sound check. It shows no significant interference, and you can now move on to the real test with confidence.
But what happens if it fails? What if your result for solution B is way outside that 0.5 to 2 lambda range? Well, that's when you roll up your sleeves and you get into troubleshooting.
So what can you do? As you can see here, you've got a few tools in your toolbox. The simplest fix, most of the time, is just to dilute the sample more. If that doesn't work, you could try using a more sensitive reagent, which lets you dilute it even further. For the really stubborn problems, you might have to actively treat the sample by adjusting its pH or even filtering it. But no matter which fix you try, that last step is absolutely crucial. You have to repeat the test to prove that your solution actually worked.
And that really brings us to the most important takeaway of all. This inhibition and enhancement test, it isn't just another box to check off a list. It's the foundation. It's what ensures the final report is built on a solid wall of evidence, not guesswork. Because in the world of science and safety, a successful test isn't just about getting an answer, it's about knowing you can trust that answer completely.